Hi, Year 11. The last section of Chapter 2 is inverse functions. And as the name implies, we're looking at functions that are inverses. Remember from your normal arithmetic, the inverse of addition is subtraction, inverse of multiplying is dividing, and they undo that operation. An inverse function is going to undo what the function did. So the function we're looking at here to start with is the function f of x equal to x squared. So our original function turns x into x squared. So 2 becomes 4, 3 becomes 9 when we square it, 4 becomes 16 when we square it. Our inverse function is going to turn our 4 back into 2, our 9 back into 3, and our 16 back into 4. What operation does that? Hopefully you've already realised or thought about it. We're taking the square root of x. So our initial points for our function were 2, 4, 3, 9, 4, 16. So now the points for our inverse function are 4, 2. So in other words, if we start with a 4, we end up with a 2. If we start with a 9, we're going to end up with a 3. Start with a 16, we'll end up with a 4. The important thing to realise here that we want to take the positive square root only, because we want to end up with 2, 3 and 4, not minus 2, minus 3 or minus 4. So this is the domain for this function. Oh, we've got that written. And here is our range for the inverse, for the function. But for the inverse, this becomes our domain. Oh, sorry. Didn't mean to undo that. So this now is our domain for the inverse function. And this is our range for the inverse function. So let's look at that graphically. Our first function, the function we're looking at originally, is y equal to x squared. And our inverse function is the square root of x. So here's a graph of y equals x squared, and you'll recognise that we've done your quadratics chapter. And if we just took the square root of all these numbers, we would end up with these values, because when I take the square root of, I think this is 1 here, if I put 1 into our initial function, 1 squared is 1. If I take the inverse, like the square root of 1, I could have got plus 1. The other option is I could have got a minus 1. So for every time I take the square root, there are 2 possible answers, either up here or down here. But we now know that that's not a function because it doesn't pass the vertical line test. And so what we do is we limit our domain. We say, well, we can't take all this part because we don't want all that part. We want to end up with a function. So we're going to limit our domain. We're only going to look at x values greater than or equal to 0. So this is our initial function, y equals x squared, and our inverse function is this one. So that's the positive square root. And that way both our function and inverse are both functions. The other thing to notice on that graph is the line y equals x. And you can see that our functions are symmetrical around the y equals x. It's like the original function's been flipped over that line to make the inverse function. So on both graphs we've drawn in y equals x. And so graphically you can work out your inverse function by simply taking the reflection over the y equals x line. So the inverse of a function is the reflection in the line y equals x, The inverse of a function must be a function. That means it's got to satisfy the vertical line test. So we may need to limit our domain so that it's true. And that's what we did in this case, where we limited our domain to only x values greater than or equal to 0. The notation we use is f to the minus 1 of x. So here our function f of x is equal to x squared. Our inverse function, f to the minus 1, is equal to the positive square root of x. If you don't have a positive sign there, that's implied. So you just write like that, you don't need to put the plus sign in. The inverse f minus 1 of a function is the reverse operation. So given an f of x, the f minus 1, the inverse function, will map the y's back to the original x's. So if this is our initial function in example 2, I've just got 3 points, 1, 3. So in other words, 1 becomes 3 in this function, 2 becomes 4, 3 becomes 5. So that's our domain for our original function. Here's our range. The inverse is the function, so this is our function. Our inverse function just simply maps it back. So 5 goes back to 3, 4 goes back to 2, 3 goes back to 1. So now, what was the range becomes our domain for our inverse function. So this is our domain now, and this is our range for the inverse function. Alright, so an inverse function is simply undoing what the function did. It takes us back to the beginning as if nothing's changed. That notation of f to the minus 1, you have seen before in trigonometry. So remember last year in year 10 and year 9, probably if we had sine of 30, then we know that that comes out as 0.5. You would hopefully remember that from your 60-30 triangle, and you're going to need to know that really well. Oops. So we'll just clear that out. Shift that over a little bit so it's not so near the edge. All right, so our 60-30 triangle, 60, 30. Do you remember the side lengths? 1, 2, root 3. So sine of 30 is a half, or 0.5. So in this case, remember, this is the angle, and this is our ratio. When we do the inverse, we've got the ratio here, and that gives us the angle. So when I do sine to the minus 1, 0.5, I get 30 degrees. Just a couple of things to note, just to watch out. If I write x to the minus 1, what does that mean? Yeah, hopefully you've said it's 1 over x. So in this case, our minus 1 is talking about an exponent, whereas our minus 1 up here, this is a notation saying an inverse function. So it's not saying take the reciprocal. So if I have 1 over sine theta, and I want to write that with index notation, we need to write it in a bracket. So sine theta to the minus 1. So that's how you show the reciprocal of sine theta, with the minus 1 on outside the bracket, not inside the bracket. Alright, so how do we find the inverse function? If we want to do it graphically, we simply draw our line in of y equals x and reflect the function around it, just flip it over. For individual points, you're just going to interchange the x and the y coordinates. So remember you saw that with this example, where here's our function. To get our inverse, we've just changed the coordinates. So the x now becomes the y, and the y becomes the x. So you just flip them, and then you can plot that on your graph. If we want to do it algebraically, it's this concept that we are changing the x and y coordinates. So the x becomes the y, and then the y becomes the x. So we can do that algebraically. So we can swap the x and y variables, then rearrange our equation, or we can make x the subject instead of y the subject, and then swap the variables at the end. So let's do an example of that one, so you can see what we're talking about. All right, we're going to do a little bit of these together. So y equals 3x minus 2. So first step is swap the variables. So now we write x equals 3y minus 2. Now let's make y the subject. So 3y equals x plus 2. Now divide by 3, x plus 2 all over 3. So that's doing it algebraically. If I want to put that on a graph, we now let's plot our original function. So this is roughly to scale. We've got y-intercept at, say, minus 2, and a slope of 3, so that's about 3. I haven't got an exact scale on it. This is the line of y equals x. So it goes through the origin with a slope of 1. So all I need now is another line which is going to intersect, goes through there. I'm just going to slope this up a little bit and bring it down so it's intersecting there. So they'll both intersect at the same place, and that's pretty close. What I'm looking at is this intercept here. Whatever that x-intercept is, which would be when y is 0, that's 2/3. So the x-intercept for the original function becomes the y-intercept for the inverse function. And the y-intercept here, which is at minus 2, becomes the x-intercept for the inverse function. So this here is minus 2. All right. All right, so we've got those, I'll just label those graphs for you so we can see those. So now when we think about our domain and range, for the domain, what values can go into the function, the original function? What's our domain? X is equal as an element of all real numbers. And for our range, y is an element of all real numbers. That's because they're both straight lines. Same story here. The input for the inverse function is all real numbers. The output is an element of all real numbers. We won't always find that's the case. We're going to see a pattern, which we'll see in a moment. So that's showing algebraically how to do it, and graphically how to do the reflection in your y-axis, and how to do the swapping of your x-intercept to the y-intercept, and the y-intercept becomes the x-intercept. Next one here, let's now do these algebraically and do them in both methods. So the first one, I'm going to swap the x and y. So y, oops, x equals y squared plus 3. Now make y the subject. Let's do it the other way. Make x the subject, then we swap. So we make x the subject. That's a B. Now swap variables. So either method, whichever one you like, you can use. So remember, we want to talk about an inverse function. And this is a graph. Our original function looks like y equals x squared plus 3. Shift this over a little bit. Not too near the edge of the board. That's got room for us. So original function, quadratic, symmetrical around the y-axis, y-intercept at 3, which you should know. I'll now draw in, this is going to be a rough sketch. There's my y equals x, perfectly straight line-ish. Our reciprocal, let me see if I can get that up a little bit closer. Okay, our inverse now is going to look like this. I need to tuck it in under. It's not to scale. Now remember, if I reflect that all the way down, if I reflect all of it, we don't have a function because it doesn't pass that vertical line test. So I need to limit my domain, so I'm going to get rid of the bottom part. So we just have the top part, which means I need to get rid of this part up at the top as well. Oh, hold on, mistake. Intercept is at 3. Hope you spotted that. All right, now we're going. So we've got to ignore this part because we're not going to have that in the bottom part. This is coming in at x equal to 3. So the y-intercept becomes the x-intercept for our inverse function. Okay, we have limited the domain. So what is the domain for our original function? What values of x can I put into this graph? Only from x greater than or equal to 0. I can have 0, that's okay. And what's our range? We're only getting y values greater than or equal to 3. For our inverse function, what's our domain? What x values can I put in? From our 3 and upwards works. So x is greater than or equal to 3. And what comes out? What's our range? Are any y values and up? So y is greater than or equal to 0. So now when you look at these domain and ranges, see how these match, except this is an x, this is now the y. We've swapped the variables. So the domain becomes the range for the inverse, and the domain of the inverse is the same as the range for the original function, but we've swapped the x and y again. But this is a 3, that's a 3. This is a 0, that's a 0. All right, so that will always happen. I don't need those dots, we'll get rid of the dots. We didn't see that in the previous example because they were all the same. You couldn't see the pattern. But now with this one, you can see that pattern with the domain and range. So there's that little, what we call the horizontal test of a function to see if the inverse is a function. So if the horizontal line cuts more than once, then we need to limit the domain for the inverse to be a function. So I've just written that out for you. If a horizontal line cuts a function more than once, then the domain needs to be limited for the inverse to be a function. right, I just want to show you this example. It's a little trickier in coming up with your inverse. So I like to do the swap x and y initially. So we get x is equal to y plus 1 over y plus 2. We now need to make y the subject. Multiply both sides. Expand. Y is on one side. Factorize. Divide. All right, we need to work out domain and range. If we go from the original function, having just done the rational functions in the previous section, this hopefully will be easier for you. So if that's our original function, then our vertical asymptote is at x equal to minus 2. Let's go red. X equal to minus 2 is our vertical asymptote because of the denominator, and our horizontal asymptote is going to be at y equals 1 because of the x in the numerator and the denominator. So our function is going to be positive, so and our x-intercept will be at minus 1. So we're going to have x is minus 2 for the x-intercept. Y-intercept is going to be when x is 0, which is a half. So that means our function must be doing this and this. All right? So domain and range for our original function. Our domain is x does not equal minus 2. Our range is going to be all y values and y does not equal 1. If we now do our inverse function over here, so this is our function, this is our inverse function. Looking at the denominator, we have our x asymptote is at plus 1, and we can now see that the horizontal asymptote is going to be at minus 2 on 1. So we've got minus 2 down here. Minus 2. When x is 0, we're at minus 1. When y is 0, we're at half. Y is 0, we're at a half. So our graph is held. Let me just check on this. X is 0, gone. X is 0, we're at minus 1. Y is 0, 2x is 1, x is a half. So our graph here is looking like that. If we think of our y equals x line, it's doing a reflection around that. For our inverse, what's our domain? Everything except x equal to 1. For our range, everything except y equal to minus 2. So again, we see matching, except the x and y's are different. All right? The inverse of the function satisfies f of f minus 1. So if we take the composite function of f and the inverse function, no matter which order we do it, we will get x. We'll work through that in class. And the other one we're going to work through in class is where we get a self-inverse. So we'll leave that to class time. Thanks for listening, and I hope you made some good notes on that one.